Hello, and welcome to this next lesson on electric field intensity. And in this lesson, we want to answer the following question. Suppose we want to find the field, the electric field, caused by a point charge, or multiple point charges. How would we calculate that? Well, we start with Coulomb's law, which we saw in the last lesson. And Coulomb's law gives us the force applied on one charge by another charge. And Coulomb's law is given as the force on point charge 2 is equal to the charge of 1 times the charge of 2 divided by 4 pi times the permittivity of free space, epsilon naught, times the magnitude of the vector that extends from 1 to 2 squared times the unit vector that extends from point 1 to point 2. Now we can use Coulomb's law to calculate the electric field caused by a single charge. And here's how we do it. We start with the charge that we are interested in, Q1. And Q1 has an electric field that sort of radiates out from it, just like that. Now, if we have another point, let's call this QT. In this case, T stands for test. We're going to call this our test charge. We can see that the force applied on T is equal to this vector. And we can calculate that as Ft from Coulomb's law. The force vector of T is equal to Q1 times Qt over 4 pi epsilon naught times the magnitude of R1t squared times the unit vector A sub 1t. Just like that. Now this force comes about because of the electric field provided by Q1. So if we wanted to remove the test charge from the equation, we could do that by dividing out Qt, and as we'll find, that is what gives us the electric field. So now we're ready to say the electric field, E, is given as just F of T divided by Q of T, which is equal to just Q, now just the one charge we're looking at, over 4 pi times epsilon naught times the magnitude of R. R is the vector that extends from the origin to Q. And we'll say R is minus RT. RT being the vector that extends from the origin to Q of T. And we know from our previous lessons that if we have a vector that extends from 1 to T, that vector is going to be equal to, if that's R, and that's R of T, then this is R minus R of T. So nothing that we haven't seen already. And that's times the unit vector, which is just equal to the vector R minus R sub T over, and that magnitude should be squared, and it's over, again, the magnitude of that vector, R minus R sub T. So here's the punchline. If we want to find the electric field caused by a charge Q at some point given as the vector R, that's going to be equal to Q times R minus R sub T, being our test vector, over 4 pi times epsilon naught times the magnitude of R minus RT cubed. And that is our equation for the electric field at a given point caused by Q. Now, before we work an example, let's ask another question. What about multiple charges? And it turns out the answer is just add them. So if we have to calculate the electric field, again, at any given point given by the vector r, that's going to be equal to the sum, as m equals 1 to n, where n is the number of point charges, of qm times r minus r sub m over 4 pi epsilon naught times the magnitude of r minus r sub m cubed. So I guess that's our real expression, right? Since this still holds even if there's only one point charge. But that's the equation that we want to work with. Let's work an example. Suppose we have 4 point charges, each with Q equals 3 nanocoulombs, or 3 times 10 to the negative 9 coulombs, and those charges are located at point 1, which is 1, 1 at 1, 1, 0, point 2 at negative 1, 1, 0, point 3, which is negative 1, 0, and point 4, which is at 1, negative 1, and 0. And we want to calculate the electric field at point 1, 1, 1. Now there's going to be 3 steps to solving this problem. Step 1 is find the vector r, which points from the origin to point 1, 1, 1. Step 2, calculate the field at P for each point charge. This will be the most time-consuming step. And then 3, add the fields together to get the total electric field. So let's get in. And like I said, this is going to take a little bit of time to complete, so buckle up. All right, step 1, find r. So we want to know what the vector r is at point 1, 1, 1. Right, now this is pretty simple because the components are all just equal to 1. So that means that r, simply put, is just going to be equal to the unit vector a sub x plus the unit vector a sub y plus the unit vector a sub z. So there we go. There's our point vector r. Now, step 2, calculate the field. So I know e sub 1, e sub 2, e sub 3, and e sub 4. So let's get into it. Let's find first the vector field e sub 1. So we know that the vector field e sub 1 as a function of vector r is equal to q1 times what we'll call capital R1 over 4 pi epsilon naught times the magnitude of R1 cubed. And the first thing we need to do is calculate our vector r sub 1, which is equal to r minus little r sub 1, which is equal to the unit vector a sub x plus the unit vector a sub y plus the unit vector a sub z minus r1, which came from point 1, which is equal to p sub 1 at 1, 1, 0. So 1, 1, 0 is going to be the unit vector a sub x plus the unit vector a sub y, but no unit vector a sub z. This means it's just going to be equal to a sub x minus a sub x plus a sub y minus a sub y, which means the only thing left will be the unit vector a sub z. And it's easy to find the magnitude. Since it's just the unit vector, all unit vectors have a magnitude equal to 1. So now we're ready to do the actual number crunching. So we write it out long form. E sub 1 is a function of vector r is equal to 3 times 10 to the negative 9 times a sub z over 4 pi times 8.854 times 10 to the negative 12 times 1 cubed. And that, when we crunch it all out in the calculator, is going to get us 26.96 times the unit vector a sub z. So that's our first electric field component. Now, we just got to do the other 3. So now let's go ahead and do E sub 2 is a function of r and is equal to Q2 times the vector capital R2 over 4 pi epsilon naught times the magnitude of R2 cubed. Now, capital R2 is equal to little r minus little r2, which is equal to ax plus ay plus az minus, let's see what 0.2 was. We'll scroll up to the top. 0.2 is minus 1, 1, 0. So that's going to be negative ax plus ay. Therefore, the vector r2 is going to be equal to 2ax plus az. And the magnitude of r2 is going to be equal to the square root of 2 squared plus 1 squared, which is going to be equal to the square root of 5. So now we're ready to calculate the actual electric field. So E2 is a function of r is equal to 3 times 10 to the negative 9 times 2ax plus az over 4 pi 8.854 times 10 to the negative 12 times the square root of 5 cubed. And if we punch all of that into the calculator, we are going to get a result that is 4.824 ax plus 2.412 az. And there is our component electric field 2. Now let's do part 3. So, a lot of the same stuff we've already been seeing here. Vector field 3's function of r is equal to Q3 times big R3 over 4 pi epsilon naught times the magnitude of R3 cubed. Big R3 is equal to r minus little r3 is equal to ax plus ay plus az minus, let's go see what 0.3 was. 0.3 is negative 1, 0. So that's going to be minus ax minus ay So that's going to be equal to 2ax plus 2ay plus az. And the magnitude of R3 is going to be equal to the square root of 2 squared plus 2 squared plus 1 squared, which will be equal to the square root of 9, which is equal to 3. Now let's go ahead and calculate e sub 3. Okay, and that's equal to 3 times 10 to the negative 9 times 2ax plus 2ay plus az. All that over 4 pi times 8.854 times 10 to the negative 12 times 3 cubed, which is just 27. And all of that is going to be equal to, when we punch into the calculator, we'll actually get that all of this business is actually just equal to 0.999 times 2ax plus 2ay plus az. So we're just going to go ahead and treat that as 1. And so in this case, we'll actually find that E3 as a function of R is actually equal to big R3, which is equal to 2ax plus 2ay plus az, right? And that's just because 0.999, we're going to round that up to just be 1 to keep some of our math simple. Now, finally, the last one, E4, as a function of R, will be equal to Q4 times big R4 over 4 pi epsilon naught times the magnitude of R4 cubed. So, capital R4 is equal to little r minus little r sub 4 is equal to ax plus ay plus az minus, let's go ahead and see what 0.4 was. 1, negative 1, 0. So that's going to be ax minus ay. So that's going to leave us with 4 is equal to 2ay plus az. And so the magnitude of R4 is going to be equal to the square root of 2 squared plus 1 squared, which is going to be equal to the square root of 5. So we can calculate our final electric field component. The field E sub 4 at point R is equal to 3 times 10 to the negative 9 times 2ay plus az over 4 pi 8.854 times 10 to the negative 12 times the square root of 5 cubed. And that's going to be equal to 4.824 a sub y plus 2.412 a sub z. And there's our fourth component there. Now, that was the tedious part. Step 3, add them. So we'll see that the entire electric field at point R is equal to E1 plus E2 plus E3 plus E4. So if we bring everything back, we will see that that's equal to E1, which was 26.96 times A sub z, plus E2, which was 4.824 AX plus 2.412 AZ plus, we need another line here, plus 2 AX plus 2 AY plus AZ. So that was our E sub 3. And then plus E sub 4, which was 4.824 AY plus 2.412 A sub z. And then if we combine the like terms, we will get that the vector field E at R is equal to 6.824 AX plus 6.824 AY. Look at that, a little bit of symmetry, plus 32.784 times A sub z. And electric fields are given in volts per meter. So there is our final answer of our combined electric field calculated for 4 point charges at that 0.111. So I know that was a long one, but there was a lot of repetition, right? No single piece was very complex. You just got to sort of sit down and take the time and do it. A lot of the problems in this course are going to be a lot like that. So if you have any questions, as always, let me know. And if not, I'll see you guys in the next lesson. Thank you.